So now it is 12 o'clock in Germany and 5 o'clock in Thailand. So welcome the contestants to the presentation today. We have the first day of a training program on Saturday. Now this is the second day. We have an honor to have Professor Dirk-Uwe Sauer from RWTH Aachen University. He will talk about electromobility in Germany. He will introduce himself as well, where he come from, and also where he's working and what is his expertise. So I would go directly to the presentation without further ado. Well, Professor Sauer, please, you have the stage.
Yeah, Professor Nisai, many thanks also for this invitation. This is really a great event. More than 100 teams is much more than I have expected, and it's really a great thing that you were able to organize this, including such a training program for the students. So as Professor Nisai mentioned, just in short, where I'm coming from, so I'm working now as a professor since 19 years at RWTH Aachen University, and my chair is about battery energy system technology, let me say. So we are looking into all the things from analytics from the material side, modeling, lifetime prediction, all the battery system design issues from the battery pack level, including battery management systems and diagnostics, integration into vehicles, but also integration into stationary applications, especially for enhancing our power system and integration of renewables. We are coming more from the engineering side, so we are not developing new materials, but we try to understand as good as possible how these materials work, and to have then optimized operating strategies, diagnostics, modeling, and lifetime prediction based on this. So we are about 80 full-time employees here at the Institute working only on these battery issues, and another around 80 students doing the bachelor theses, master theses, or working as student assistants here. So just maybe to show what is our main challenge right now, because just these days we are moving to our new research center with a total of 5,000 square meters of lab space and office space, where we can look into batteries on the one side, really on a nanometer scale with electron microscopes and computer tomographs. And on the other hand, we have temperature chambers where we can test full cars if we want to. And we have both here batteries and power electronics together. And it's just impressions, and we're just in the phase of moving into this building, and by the end of this month this will mainly be finished as far as it looks like right now. And I just want to make you aware, and maybe this is also interesting for you, that our work is not only purely for the academic side. We always work very closely with companies, but we also have founded companies. There are 4 successful spin-off companies working these days around our university group, and they have in total more than 120, 130 full-time employees here. And this is very interesting also because lots of the people who finish their work at our institute can continue working in there. So now let me have a look into the topic. It is simply called electromobility in Germany. For sure, Germany is not on its own, so I will have a look for sure also into some numbers regarding the European Union or also world. But yeah, let me have a look into this first of all, also by letting you know what the boundary conditions are. And the most important thing is that Germany has decided to be emission-free, net zero emission-free in the year 2045. The European Union has a target of 2050. So, and this seems to be a long while to go, but it is absolutely not if we look, for example, on the lifetime of vehicles. And let me show what the problem is. Yeah, so we still have a huge emission of CO2. It dropped somehow from 1990 to 2020, but it is still something like more than 7 point or almost 7.7 tons of CO2 per capita. For as a comparison, China currently has about 7.4 tons per capita. So while at least our emissions went down to a certain amount, in China it is still going up, because for sure the level of industrialization is still increasing. But this is a challenge we are dealing in the world. So we overall have still increasing emissions. However, in Germany, this is where we had the emissions in the past. So the red bars is the energy sector, yellow is industry, blue is buildings, mobility, and dark blue farming, and green and some others. And now the target for 2030 is to reduce by minus 65% compared with 1990. But you also can see how strong the emissions have to go down from today towards 2030. So in 2021, we had approximately 768 million tons of CO2, and this should go down to 438 in 2030, down to 150 10 years later, and as mentioned, to zero in 2045.
Professor Sauer,
Yes.
I have the notification from our translators. Would be nice if you could a bit slower.
Even slower.
A bit slow, or you can make a pause. Yeah, you can speak and make a pause of 2-3 seconds added between sentences. Would be nice.
All right. So to get CO2 free, we have to change our energy system really dramatically. Today, we have a fossil-fueled energy world, all of us in the world, based on gas, coal, and oil, mainly some nuclear fuels in some countries in addition. And these fuels are typically all burned. So we make heat. And from the heat, we can make steam for power generation and power plants. We may do combustion in combustion engines, or heat for whatever. But it is mainly using the fossil fuels to burn them. And this will be very different in the future. In the future, we will have mainly electricity as the primary energy source. Wind and PV systems are will dominate our energy supplies. Some additional sources, okay, but dominating will be wind and photovoltaics. And they produce power, first of all. And electrical power is the energy with the highest value. We can do everything from electrical power: mechanical force, light, communication, whatever is needed. And this is the reason why we are thinking about electromobility. because we want to make use of this source of electricity at the highest possible efficiency. And when we look to different sectors, according to the German energy law, we can see that the law says we should decrease the emissions in the mobility sector by more than 40% from 2020 to 2030. More than 40%. This is really huge in numbers, and we're not really sure how this could take place, but at least it is clear without electromobility, it will not work at all. Now, the European Commission is just in the process, and processes in European Commission or European Union are very complex and take a long while. But meanwhile, it is quite clear that our Parliament, the European Parliament, as well as our national governments have decided that more or less completely combustion engine cars are banned from 2035 with regard to newly sold cars. So if you still have a combustion engine car, you're allowed to use it further, no question. But new registrations of combustion engine cars will be banned in the European Union latest from 2035 onwards. There's just 13 years to go. And this is necessary because with a very simple calculation, I would like to show you that it takes a long while until all the combustion engine cars are off-road and therefore will not use fossil oil anymore. The green curve shows the anticipated percentage of electric vehicles among all newly registered cars in the years. So in 2030, we expect roughly 80% of the newly registered cars will be full electric. By the way, this is a number which is achieved already today by Norway. Norway is for sure a much smaller country, but they have started into electromobility with much more emphasis earlier, and they already have 80% of all newly registered cars as combustion engine cars without any problems in infrastructure for charging and so on. So in 2035, it ends then with the combustion engine cars. So 100% of the newly registered cars must be electric. However, if we assume that a car lives 15 years maybe, then we get the blue curve. The blue curve shows us how many cars compared with today, or how many combustion engine cars compared with today, 100%, are still on the road. And you see in 2030, it will be still more than 80% or about 80% of the cars will be combustion engine cars. And even in 2045, there are 3-4% left, assuming these 15 years lifetime and assuming that no other measures will be taken by the government. And this is a reason why starting now to really go strongly into electromobility is already the latest point in time to meet the necessary targets with regard to CO2 emission reductions. So beside this, and I would like to make you aware of this, even you're probably quite a bit away from Europe at the moment, we have several challenges in the European energy market these days. First of all, we have implemented a CO2 trading mechanism more than 10 years ago. But for a long while, the cost for a ton of CO2 were very low, sometimes as low as 5 euros per ton. And even in 2020, you can see it was on average maybe 25 euros per ton CO2. Whereas in the last part of last month of 2021 and now in 2022, we have achieved 80 to 90 euros per ton CO2. This has an impact on power price. For example, we produce maybe 20% of our electricity from lignite, so brown coal, which is the only energy resource we have naturally in Germany on our own. And the production cost of power from lignite is about 3 cents per kilowatt hour. Now, having 90 euros per ton CO2 adds another 10 cents just for the CO2. So the price for power from a lignite power plant increased from 3 cents to 13 cents, which is a tremendous increase. And beside this, and even more severe, is the problem with the exploding cost for natural gas. The prices for natural gas started to increase already in the second half of 2021 and then got to a next maximum when the Russian aggressive war to the Ukraine started this year. And meanwhile, or let me say, Europe gets about 1/3 of its energy in coal, oil, and gas from Russia. But due to the embargoes on the one side, and because Russia is now turning off the gas supply via pipelines to a very large extent, we suffer from under supply of energy and especially gas. And this increases the power production dramatically because most of the time the gas power plants set the price for all the other power plants. And the gas price further increases. It was in the past something like 10 to 20 euros per megawatt hour. But meanwhile, the futures for 2023 are traded at 90 euros per megawatt hour. So a factor of at least 4.5 times more than a year ago. And even for 25, the traders expect to have prices in the range of 60 euros per megawatt hour in gas. And this affects a lot our power industry, and the prices for the end users will dramatically increase, and it also affects the industry very much because the industry relies very much on the use of gas. In addition, we see another problem in Europe because France, which is supplying themselves typically with 80% electricity from nuclear power plants, has shut down more than half of their nuclear power plants at this point in time due to plant revisions, but also due to unexpected failures with corrosion in critical systems. And therefore, France during the summer and probably also during the coming winter has a significantly reduced power production and needs to be served in addition, especially from Germany, which requires additional coal and gas power generation. To overcome this, we are going for a very strong expansion of our renewable power generation. The government has targeted to get towards 80% of power production from renewables in 2030. And this will require a very strong increase in new installations. So where in the last year we had about 5 gigawatt newly installed PV, we have to increase this in the coming years to 20 gigawatts per year. And in wind turbines, we were very low in the last year in the range of maybe 1.5 gigawatt, and we have to increase this by a factor of 10. But this is the only way we can overcome in the medium term, on the one hand, our power supply issues, and on the other hand, also to get at least close to our CO2 reduction targets. Now, this diagram shows that with increasing feed-in from wind and photovoltaics, we definitely have lower prices than at low feed. On the x-axis, you can see for each point of this year, the feed-in from wind and PV in total. And you may know that, or you have to take into account that the peak load in Germany is about 80 gigawatt. And on the y-axis, you see the power trading price at the power exchange. And you can see clearly that there is a very strong correlation with decreasing prices at the power exchange when the feed-in from renewables increases. So the renewables, or the change, the Energiewende, the change to renewables is not the root cause for our price problems. The renewables is the solution. We now have to go much faster than in the past for. However, we're now producing green electricity, CO2-free electricity. The question is what to do with this. Because we have to serve for sure our energy system, but mainly we want to reduce emissions. And now we can calculate how much emissions can we save, how much CO2 emissions, if we use 1 of the kilowatt hours from green power generation. And this table shows you if we turn down a lignite-fired power plant by replacing the kilowatt hour from renewables, we can save 1.15 kilograms of CO2. If we drive, or if we use electricity to drive a battery electric vehicle instead of an internal combustion engine with petrol, then we still can save something like 670 grams of CO2. If we would use fuel cell cars, so producing hydrogen first from this green electricity, then bring it into the car and reconverting it to electricity in a fuel cell, then we only can save 260 grams of CO2. And if we even would make a synthetic fuel, means we are producing hydrogen, and then we take some CO2 from the air, and then we can produce any type of hydrocarbon, so which are chemically identical to a natural gas or oil or gasoline or diesel. Then we just can save something like 160 grams of CO2. And you can see from these simple numbers, and I will show you them again on the next slide, that going for electric vehicles simply reduces emissions much more than any other way. And this is shown in this diagram here now, just in another way. It lists efficiencies. So if I use a battery electric vehicle and I would like to have 1 kilowatt hour of driving energy, then I have to bring about 1.3 kilowatt hours of green electricity. Then we have losses in the power grid and the charger. During discharging, we have some losses, and we have losses in the power converters and electrical machine. But overall, about 74% of the energy we provide from renewables can be used in the vehicle. If we go for fuel cell electric vehicles, we have to produce hydrogen at a certain efficiency. We have to compress the hydrogen. We have a limited efficiency in the fuel cell. And again, we have the inverter and the electrical machine. But as you can see, the overall efficiency is only roughly 1/3. So 3 kilowatt hours needed here as input and only 1 kilowatt hour output. And it's getting worse if we are going for these e-fuels or synthetic fuels, because it requires not only producing hydrogen, it requires also from capturing CO2 from the air. It requires a chemical process to produce the liquid hydrocarbons. Then they also need to be transported. The combustion engine has maybe an efficiency on average of 30% in vehicles, in passenger vehicles. And this means the overall efficiency is maybe only 14%. Some say it is even lower. So this is a clear reason why for the passenger cars, we see worldwide the battery electric vehicles as a dominating technology. The hydrogen-based systems might be an option in buses or heavy trucks, but this is something we might discuss towards the end of the presentation. So some aspects on mobility. First of all, the design of electric vehicle has really changed a lot in the last years. We had let me call the first generation of electric vehicles from the main car manufacturers, of the traditional car manufacturers, which were launched, let me say, about among 2012 and 2018 maybe. These were conversion design cars. You can see here a Golf, so the most sold car by Volkswagen. And this was originally here a combustion engine car, including gearboxes and transmissions and so on. And they just removed the conventional part and fit the electric drivetrain and the battery in the remaining space of the vehicle. And you can see the complexity here. And every piece of open space was used somehow, but this is not efficient in design and not cheap at all. And what we see these days, and introduced already from the very beginning by Tesla, but meanwhile taken more or less by all car manufacturers, is what we call the surfboard design. So we have in the ground floor of the car a battery with a height of only 12 to 15 centimeters maybe, and there is plenty of space for the battery with driving ranges in the order of 300 to 500 kilometers. And then we have power electronics and electric motors, either centralized on the axis, rear or front axis, or directly in the wheels. This depends on the specific concept. But you can see immediately the very different types of design, and what we have as a modern drivetrain. And by the way, on the platform, you can put many different types of cars. which increases also the number of these drivetrains and therefore drive down cost, is what makes the production much cheaper than what we had in the first generation. And the expectations of the large European and United States manufacturers are that the cost for a full battery electric vehicle will equal more or less a comparable combustion engine car already in 2025. In China, we have already these days, on average, lower cost, slightly lower cost for a battery electric vehicle compared with combustion engines. And this is the same, just from a different perspective. You may have a look into this when you look to the slides once again. There's not much new here in this slide, just gives you another view on the electric components and the battery system. So now what we can see is that the number of electric cars which are meanwhile available is increasing. Here on the y-axis, and this is not totally right here, this is the number of different models. So worldwide, we can see in 2021, there were offered more than 440 different models of electric vehicles by all the different car manufacturers worldwide. And about 2/3 of these are full electric cars, and 1/3 are plug-in hybrid electric vehicles. And we also can see in this diagram, which refers to the right scale, the range, the typical range of these cars for the plug-in hybrids in yellow and for the full electric vehicles in green. But I have this curve on this diagram already starting in 2010 once again. And you can see, while the first full electric vehicles had driving ranges on the order of 120 to 150 kilometers, it is meanwhile, on average, 350. The plug-in hybrids, which have a combustion engine for the long distance driving, have still driving ranges in the order of 50 to 60 kilometers from the battery. This is for most of the driving purposes sufficient, but only if you want to go long distances it is not, and the plug-in hybrids still have a combustion engine and they use fossil fuel, at least on the longer distances. But this tremendous increase in driving range at still decreasing prices, by the way, is the most important factor that battery electric vehicles are meanwhile also a real success in the international automotive markets. And this diagram shows you the overall global stock on electric cars, so the total number of cars which is on the roads. And we can see in 2021 that China on its own has about 6 million full battery electric vehicles and another 1.5 roughly plug-in hybrid electric vehicles. Markets are followed by Europe with a higher share of plug-in hybrids. United States is still much lower, and the rest of the world, the other countries, have relatively small numbers of electric vehicles yet. But we can see that the market is driven mainly by China and by Europe, and to a smaller extent by the United States. Japan, for example, is not really of major relevance yet in this field of full electric vehicles. This is now a look somewhat closer into the different regions, China, United States, and Europe. And here we now can see the bars showing the number of sales in these markets in these years. So it's not the overall stock, but the sales per year. And you can see it sums up to about 3.3 million cars in China in last year, resulting in the green dot here is a market share of about 16%. This is everything else but marginal. So this is, meanwhile, a very important part of the business of the car manufacturers. And in Europe, you can see, mainly dominated, by the way, by the German market, about 2.2 million new registered cars with a market share at around 17%. In the United States, the market share is about 5%. As mentioned before, there is somewhat behind Europe and China. And here now you can see the numbers for the individual or for some selected countries. Germany here was a market share of above 25% in the last year, and a total number of sold cars in the order of 660,000 cars, roughly. France, United Kingdom are relatively similar. Then we have some other countries, and you can see indeed Japan, with a rate in the order just of 1%, is quite low with regard to electric vehicles. So these are the numbers, just in a different way to represent them. And I just want to point out that you can see these are always the numbers for the newly registered cars in the specific years, that the number of sold cars is really increasing a lot. And as I said, in 2030, it should reach up to 80% in the share, and already 5 years later should achieve 100%. So this for sure will require huge capacities in batteries. We expect that the worldwide market for batteries in electric vehicles will be about 1,000 gigawatt hours per year, somehow among 2025 and 2027. Just as an example, about 2013, Tesla announced to build a gigafactory for battery production. And the announced capacity at this point in time was 30 gigawatt hours per year. And this equaled, at this point in time, in 2030, the whole battery production in lithium-ion batteries worldwide. Now we are talking not about 30, but 30 times more than this. So 1,000 gigawatt hours. And just Volkswagen intends to build in Europe 6 factories with 40 gigawatt hours per year each. So Volkswagen wants to get to a production capacity in batteries in 2030 of 240 gigawatt hours just for Europe. The overall market in 2030 is expected to be about 3,000 gigawatt hours battery capacity for the mobility sector. So something about charging infrastructure and also vehicle-to-grid potential. Because obviously, when changing over from gasoline and petrol and diesel cars to electricity, we need simply more options to charge these batteries or these vehicles. And when looking into the charging infrastructure worldwide, we can see already quite a bit has been done. So on the left-hand side, you can see in thousands here the number of so-called fast charging stations, whereas everything which is above 22 kilowatt is accounted here as fast charging. This goes up to 350 kilowatt in the European system, which is the infrastructure which is now under construction, especially alongside the highways to allow the upper class cars to get charged in something like 10 to 12 minutes for a driving distance of 400 kilometers. But you can see as well that China is really going into this, with the vast majority of the chargers are operated in China as well, the fast chargers, as also the public slow chargers, so everything which is up to 22 kilowatt. On top, and this is very special also in Germany, you have a lot of non-public chargers at home, because the vast majority of people is charging their car at home, at least right now. And therefore, these lists are only listing the public charging infrastructure. And again, you can see China has the vast majority, followed by Europe, and then smaller shares in the United States or all the other countries. And this is a diagram which shows here how much kilowatt of charging in public chargers is available per electric vehicle. And you can see these blue bars showing how much kilowatt hours are really available here, with New Zealand on top. Norway with its very high share of newly registered cars, 80%, I have mentioned this, more than 3 kilowatts in public charging infrastructure. German at about 2.5 here. And this is how it goes. China was somewhat less than 1 kilowatt. However, this is mainly due to the fact that China has such a huge number of electric vehicles on the road meanwhile. And the red dots give you the number of electric light vehicles. So this includes not only the passenger cars, but also light duty vehicles of any type. Tells you how many vehicles a country has per charging point. For Germany, for example, about 8 cars come for 1 public charging station. And this will be sufficient. Not more than this is needed. This will probably decrease in the future. And what is interesting in this is that for sure these electric vehicles also drive around huge battery capacities. And most part of the day, these batteries just standing around. A car is driving only 1 to 2 hours on average in the European or in the United States market. So 22 hours a day, this battery capacity would be available also for doing grid services. And when we look into the German market, just by the end of 2021, we had in electric vehicles about 40 gigawatt hours of battery capacity. This was only 2.5% of the vehicles were electric of the overall stock, but this already equaled to 40 gigawatt hours. And the number is interesting because all our pumped hydropower stations in Germany which are responsible for balancing the grid and grid stability, also have a capacity of 40 gigawatt hours. So in very few years, we have brought a capacity equaling the total pumped hydropower station capacity on the road by electric vehicles. And if you count the charging power of these car batteries, this is even much higher than for the pumped hydros. Because if we wanted to, we could charge and or discharge these, or charge at least these batteries at this point in time with more than 40 gigawatt power at a time. This is what we will never do, because this is nothing what our grid really can balance. I mentioned earlier, the peak load in the German grid at the moment is just 80 gigawatt. So 50 would be too much. But it shows the potential for grid services. Because these 40 gigawatt hours of pumped hydropower stations only have power generators of 6 gigawatt. So very much less power, and especially for strong fluctuations, we need more power installed than energy. And what is also interesting, when we look around in Germany into the fields of stationary batteries, newly installed stationary batteries, mainly dominated by lithium-ion batteries, then we can see that only about 10%, this is this orange part here, about 10% of the overall newly installed battery capacity is stationary, and 90% is in the mobility sector. And this is what makes it so interesting about thinking of the battery capacity from the cars via the vehicle to grid concepts. And by the way, Volkswagen now has started this year to equip all new full electric vehicles with a bidirectional charger. So this is the first and important step to a full grid service capacity from electric vehicles, because these bidirectional chargers allow us not only to charge the battery, but to feed electricity also back into the grid. So if the grid is weak, we can support it, or we can buy cheap electricity by charging the battery in times of low prices, and at high prices we even can sell, as long as we don't need the battery for long distance driving. But the average driving in Germany is 37 kilometers a day, and as we have seen, the average size of the newly registered cars on a worldwide level is already in the order of 350 kilometers, so 10 times more than what a typical user needs. So in short, something on lithium-ion batteries. This is for sure not a German individual, but just to give you a short look into battery technology. This is what we call a Ragone diagram. It gives us an idea about the energy densities of different battery technologies. We have the gravimetric energy density here on the x-axis. This tells you more or less how much energy you get per kilogram of battery, or if you know the weight of the battery in your car, it tells you how much energy you get, and therefore you can calculate the maximum range. The numbers given here are energy densities on a cell level. On a pack level, including management systems, switches, cooling, housing, and other safety relevant things, the energy density surely goes down by maybe one third. And on the y-axis, we see here the power density. It tells us how fast we can discharge the battery, or also how fast we can charge it. And this, in the discharge case, it tells us how much power we can give to the electrical machine. And we can see from this diagram that the lithium-ion technologies, and there are many different of them, in light blue shown here, is dominating all the other technologies. And as they are also quite or very good in terms of lifetime and in efficiency, the lithium-ion batteries really rule the markets here in the mobile sector anyway, but also in the stationary sector for the new applications. Some other older markets are still in the hand of lead-acid batteries. And if we look into such a lithium-ion battery, we can see such a layered design. And this is a light microscopic view on a cross-section of a lithium-ion battery, where we have the anode here on the right-hand side with a copper current conductor, a thin foil in the center, and it is pasted here by graphite on both sides. And we have a separator, which assures that we don't get short circuits among the two electrodes. So the separator must conduct, on the one hand, ions for the electricity pathway. But on the other hand, it is most important that the separator has really 0 holes. We cannot accept even a single hole, because this would cause immediately a short circuit in the battery, and this would destroy the battery. And the left-hand electrode here is the cathode, so with a higher potential compared with the anode. And it has an aluminium conductor as a foil in the center, and it is pasted then by the different kinds of active materials. The active materials could be here nickel, manganese, cobalt oxides, could be lithium iron phosphate, or other variations of lithium oxides, lithium metal oxides. And this is how such a battery works. Now we have the anode on the left-hand side, and we have the cathode on the right-hand side. And when we start discharging the battery, then the lithium ions get rid of an electron, which goes through the outer circuit to drive an electric motor, for example. And the lithium ions diffuse from the anode through the electrolyte and the separator towards the cathode. And this is what is called an intercalation battery, because both electrodes are so-called intercalation electrodes. This means their crystal structure remains unchanged during the charging and discharging. The graphite structure remains, but also the metal oxide structure we have here remains, and just during discharging, the lithium ions are going out of the anode material and they diffuse into the cathode material. And during charging, things are just the other way around. During charging now, the electrons go the other way around, and the lithium ions go from cathode to anode. So in the finally fully charged state, the anode is completely filled with lithium. whereas in the cathode, only a certain part remains in the order of maybe 30% in the conventional lithium metal oxide for safety reasons. And this is just a picture, a view into the active material and on a micrometer scale. And you can see here graphite particles, you can see CNTs so carbon nanotubes, for example, in some batteries for not storing the energy, but for improving the electrical conductivity of the active material. And here we have the active material. Sorry, the graphite here is also for conducting issues. These are the active materials. NMC stands for nickel, manganese, and cobalt. Now, if you look further into the batteries, you will see that even if a certain material is known by name, and here is, for example, the carbon or the graphite electrode of 5 different batteries. All pictures were made with the same equipment and had the same scale, and they all are called graphite electrodes. And I think you can see already from these pictures very easily that the graphite structure is very different. And the graphite structure itself is relevant for the properties, for the electrochemical properties. Very small particles, for example, give lots of surface and therefore higher rates in charging or discharging. But unfortunately, also the main aging processes take part on these surfaces. So the higher the surface is, the faster the battery ages. So as in many other cases, to find the right composition is a question of compromises among different features, such as charging or discharging rates, or on the one hand, or lifetime and aging on the other hand. And just to give you a few of the different combinations which are used these days, we again have here the graphite on the right-hand side and the cathode on the left-hand side. And today, commercially, you can get these NMC batteries, cathodes, nickel, manganese, cobalt. LCA is lithium, cobalt, aluminium, and LMO is lithium manganese oxide. Yeah, these are common abbreviations, and sometimes you can read on the nameplate or in the data sheet which chemistry is used. But we also have found a lot of batteries where the reality inside the battery equals not what is in the data sheet or on the nameplates. Yeah? We can analyze this in our lab in detail, and we were surprised in several cases what we found compared with which was on the nameplate. Another quite popular material is lithium iron phosphate, LFP, which is another version for the cathode material. But please be aware that the anode, the graphite anode, still remains the same. And the anode, for example, is mainly responsible for the lifetime. And therefore, if you just keep the graphite in the same amount as with an NMC battery, you will not get more lifetime with an LFP battery. Nevertheless, LFP is interesting because it is more safe than the nickel, manganese, cobalt oxides, and it is generally could be cheaper because iron and phosphate compared with cobalt or nickel are really cheap. But the disadvantage of lithium iron phosphate is that the energy density is 25% to 30% lower compared to best NMC battery technologies in class today. So LFP, more safe, maybe cheaper, but definitely at lower energy density. And then there are many other things under development, but one is maybe also interesting because it targets in getting rid of the carbon. Because what I haven't mentioned yet is that the carbon itself has 10 times more weight than the lithium, which is stored in the anode. So 9 out of 10 weight units in the anodes today are graphite. And the graphite is used only for safety reasons, but is not really increasing the energy density. The energy density is given only by the lithium. And the highest energy density can be achieved, obviously, if we would have a pure metallic lithium electrode. But this is something which is not working with today's liquid electrolytes, because the liquid electrolytes used and the metallic lithium will have a strong and ongoing electrochemical reaction, which will age the battery in very short time dramatically. Therefore, people try to get in what they call the solid state batteries. And in fact, what is changed then is that the today's used liquid electrolytes are replaced either by a polymer or a ceramic solid electrolyte. And this would allow then combining such a solid electrolyte with metallic lithium. There are a huge number of challenges on this pathway, and therefore we do not really expect that until 2030 these solid-state batteries will become an important player in the field of lithium batteries for cars. But maybe in the long run, it might get interesting. What is more interesting and not listed on these slides is that battery manufacturers, and especially the largest one of them, CATL from China, have announced to come up with sodium-based batteries. So in a first approximation, the lithium is then replaced by sodium. And sodium obviously is much, much cheaper than lithium, and therefore an interesting replacement material. But we will see what the performance of these batteries is. We expect energy densities, for example, in the range of LFP, so 25 to 30% lower than the NMC batteries. But for the medium type cars and those with ranges maybe up to 350 kilometers and not 500 or more, the LFP and the sodium-based batteries could be sufficient. So then I would like to have a short look into fuel cell electric vehicle market. I mentioned already that the efficiency is much lower, and so are also the number of registered vehicles worldwide. Here you can see a diagram from the International Energy Agency. Within the outer circle represents the shares of the worldwide installed fuel cell electric vehicles. So these are not the newly registered cars. This is the overall stock. And you can see that Korea here is dominating. Out of about 50,000 fuel cell electric vehicles, more than 1/3 is in Korea. And still 13% in Japan. Remember when we looked into the number of registrations of full electric vehicles, which account meanwhile to more than 60 million, Korea and Japan were very low. So they still dream the dream of fuel cell cars, and therefore they did not go in the same way into battery electric vehicles like China, Europe, or the United States. And for sure, you also need filling stations. And you can see here, out of about 730 worldwide hydrogen filling stations, close to 10% are in the United States, 20% in China, 16% in Korea, and 13% in Germany, with only a share of 3% of the vehicles. Also in Germany, there is still a lobby for fuel cell vehicles, and some people who can afford it try to buy such a car, but the numbers are really extremely low, and it makes no sense to really build the hydrogen filling infrastructure for passenger cars here. So these are just quite similar numbers. However, here now we don't have we have the vehicle stock by region in 2021, once again with Korea, United States, and Japan dominating. But it is different if we look to buses and trucks. So China has about 4,500 fuel cell buses, but I think several 100,000 full electric, battery electric buses. And trucks, another 4,000 somewhat. And you can see only 100 trucks are in all the other countries of the world. And the buses, at least we have about 100 in Korea, United States, Japan, Germany, other countries. But these are more for testing purposes rather than really of relevance for the public transport. And I also would like to discuss you what could be beyond, or how could we drive our trucks, especially heavy trucks, 40 tons or more of heavy trucks. And there we have 4 different concepts. And there it is not really clear yet where we will end up. There is one option to use the synthetic fuels. But you remember the efficiency in producing synthetic fuels is very low. And therefore, I hardly find truck manufacturers who really rely on the green synthetic fuels, because the fuels would be much too expensive due to the low efficiency compared with other options. Next options is with fuel cells. I showed you there are about 4,500 trucks worldwide, which is still neglectable for sure, but for testing purposes, having hydrogen as a main source of energy, and which could give them maybe one day of driving with hydrogen. There are prototypes presented by different manufacturers. Some of them are still on the market, some of them already are bankrupt, so difficult business till now, not only for the fuel cell trucks, but also for the battery electric trucks. And here are some more things about hydrogen filling stations and also buses. And the third option is to go with an overhead catenary. So simulating somehow the power supply of trains with overhead lines, but having them on roads, like you can see in these pictures. These are test highways in Germany and Scandinavia, where you have the overhead lines here, and the trucks take electricity from the overhead lines, similar to trucks to trains. The only difference is, as you may see here, as an electrical engineer, you will recognize immediately they have 2 connections to overhead lines, not only one as a train. The reason is simply the trucks driving on rubber tires, and they have no conductivity to the earth, whereas trains have steel wheels on steel railway tracks, so they simply use as a second pole the tracks rather than a second overhead line. And finally, we could go also for full electric battery electric trucks. Sounds a little bit crazy maybe at the beginning because you need a lot of batteries in such a big truck. But if you look to Europe, for example, the trucks are allowed to drive for 4.5 hours, and then by law, the driver must make a break of at least 45 minutes. And if we use these 45 minutes to recharge the battery, which is not a high charging rate, but a high charging power for sure at about 1 megawatt, we can recharge the battery in 45 minutes quite easily for another 4.5 hours of driving. And this is okay. And the batteries for sure are heavy, maybe 5 tons, maybe 6 tons, but 90% of the trucks on European highways are not limited by weight in their cargo, but by volume. So the cargo space is simply full in volume, and only less than 10% of the trucks are limited by weight. So the majority of the trucks could easily afford the additional 5 tons of batteries, and they could go with this. And this is a real fight. So we have in Germany 2 world-leading truck manufacturers. The one is Daimler, with many companies belonging to them in Japan, in the United States, and other countries. So the largest truck manufacturer of the world. And they still say the long-haul heavy trucks will go on fuel cells. But they also develop the battery electric vehicles. This is what we know. The other one, which is called MAN, is also a large truck manufacturer. And they have decided already many years ago that they will go purely on battery electric vehicles, on battery electric trucks. And the reason is, on the one hand, the hydrogen as a fuel will be much more expensive than electricity in the long run. And they say also infrastructures, for example, in African countries, is much easier to build up with electric chargers rather than with hydrogen filling stations. So summing up, I tried to show you currently we have very high electricity prices in Europe, which is for sure not very good also for introducing electric vehicles. But we plan to increase the share of renewables in power production until 2030 to 80%, alongside, by the way, with a 20% increase in power consumption. So we need more electricity for mobility, for space heating, and so on. So electricity consumption is not expected to go down anymore. The market for electric vehicles really grow fast. Dominating are the markets in China and in Europe, followed by United States to a smaller extent. Other countries in the rest of the world are significantly below. Germany would like to terminate the sales of combustion engine passenger cars by 2035. Combustion engines may still be there for farming machines, for example, or maybe construction machines. Also, trucks are not included in this, heavy trucks. Light-duty trucks, yes, but they go to battery electric anyway for different purposes, for the different reasons. Lithium-ion batteries and all the derivatives rule the battery world and will do so for a long while. And passenger vehicles, we don't see any alternative to have them as battery electric vehicles in the future. And the hydrogen will become an important carrier. So hydrogen will play a major role in future's energy system, but mainly for industry, for the power sector, and for, as already mentioned, some special applications like, as I said, farming machines, maybe construction site vehicles, ships, airplanes, and so on, but not really in road transport. And by this, I come to an end, even though I was not able to hear, I would like to say many, many thanks to the translator, who surely had a hard job in the last 5 quarters of hours. And nevertheless, I hope there is some room and possibility for having some questions here in this session now.
Yeah, thank you very much, Professor Sauer. Very nice presentation and very detailed. Maybe for the students, some technical terms may be not so familiar for them, but I would like to give the 15 minutes for them to ask any questions. So the questions can be put into channels. Yeah, you can ask in Thai, yeah, or type in the Thai channel, and then the moderator over there will send the text to me, or the attendants in this room, you can raise your hand and ask directly. Yeah, let us start first with the first question from this room. Is there any question from this room, please, in English? Or you can ask in Thai, I can translate if you like.
Could I ask a question?
Yeah, please.
Thank you. So in the future, there is going to be a large amount of lithium-ion batteries. So I want to know if there is any plan for the large amount of lithium-ion battery that's going to be disposed in the future, and would it affect if in like 10 years, maybe this disposed lithium-ion battery will be obsoleted? Thank you.
Yeah, many thanks for this question. This is for sure a very important point. We do not really expect a shortage of lithium in 10 years or 15 years from now, but we expect a shortage in the coming 3 to 5 years. And the reason is simply because the car manufacturers have announced in the last 2 years such extreme increase rates in cells and plant cells of electric vehicles that the mining capacities hardly were increased in the same amount during these times. Australia was investing a lot into this, and they increased their production dramatically, but especially South America, where the largest resources are, is still quite a bit behind. Nevertheless, for sure, the recycling is also most important. European Commission has set up laws which define very detailed which share of battery materials must be recycled, and they also define how much the share of a new battery from recycled materials must be in the future. However, one could show very easily the recycled materials will contribute to the new lithium-ion battery production even in 2035, less than 25%, because the batteries live 10 years maybe in the field, and we're just starting to ramp up. And for sure, in 2032, in 2032, we can have only those batteries available for recycling, which are produced today. But today, the market still is relatively small, so this will change. So, yeah, cobalt, nickel, lithium, copper, and aluminium will be recycled from the batteries. But we are not really sure which of these materials are needed in 15 years from now. But at least it is clear that all batteries must be designed for full recycling.
Yeah. So
thank you for the clear answer.
Yeah. Okay, next question, please.
Another question, please.
Yeah, please.
How do you reduce the emission of carbon dioxide by the production of lithium-ion battery in EV cars?
Yeah, this is for sure same relevance here. We are not only going for reducing emissions in the mobility sector, but for sure also in all other sectors. I haven't discussed this here because we were looking to mobility, but also the German industry, but also industries worldwide have to reduce their emissions by using green energy. And we can see this already very well in Germany and Europe, that the companies, Tesla, for example, built a gigafactory for cars and for batteries in Germany just the last 2 years. And they placed it exactly where we had very high shares of renewables, because they want to use clean energy for the production of the batteries. And same goes on for mining activities. The mining companies also thinking now how they can replace combustion engines and oil use in mining processes. You always should be aware that at least the main countries in the world, the industrialized countries, have to be down to zero emissions in 2050, and this still will not really save the climate. And I think I must not tell anybody in Thailand what it means if the sea level would increase for a few meters more. So we have to go down in these emissions, and this for sure then goes along the full production line. And therefore, by reducing the emissions in all sectors, definitely immediately we also reduce emissions in the battery production. But by the way, producing a hydrogen storage tank, compressed hydrogen gas at 700 bars, which is used today normally, is using more or less exactly the same amount of energy compared with battery production. So fuel cell vehicles are not better in this category at all.
Thank you.
Yeah. Next question, please.
I would like to ask a question.
Yeah, please.
I was wondering, like, is there the battery 80 is until 80% of capacitor, it will be rechained, right? So it means that we recycling the battery, but there are some waste. So what are the difference with the combustion engine? Because in the end, there's still some waste, and we are being in the same loop of using like the engine with the combustion engine.
Is it clear enough for you, Professor Sauer? Is the question clear enough, or we could repeat
Maybe
the
not
question?
completely. It was it's about the 80% end of life. Is this right on the one hand?
I mean like the battery. Actually, the battery, they have the period of using it, right? So they have some waste. So the waste that we get from the battery is will increasing in our earth, right? So what they have some kind of effect on the environment, right? So I was wondering that we are doing in the same loop of the combustion engine, because doing the process of creating the engine, the car, we have some waste, of course. So it means that we are increasing all the waste in our earth, right?
Right. Indeed, as I have mentioned, we need raw materials and we need energy for producing batteries. No question. Yeah. So nevertheless, we know that the majority of the emissions come over lifetime. First of all, so the emissions from the production of conventional cars and even more energy in battery electric vehicles is still low compared with the emissions during the lifetime. And therefore, the overall emissions are quite low with electric vehicles if green energy is used. If you use electricity from coal power plants, then the overall emission balance is not very good. This is no question. So electromobility makes sense if we have a clear pathway towards renewables and emission-free power generation. And then, indeed, so we need recycling, bringing back the raw materials into what we call the circular economy. And this is of interest for different reasons, especially on the one hand, due to these ecological issues you just have raised, but also because countries like Germany or other European countries do not really have these raw materials on their own. So to become a little bit less dependent, we also really want to go much more into the recycling than in the past. And it will be not only the market which rules the recycling, it is really laws which define very clearly the rates of recycling and the recyclability of the concepts in general.
Yeah. Okay. Is it clear enough? Or yeah, if the answer is not clear, you can put further questions or ask for further clarification. Yeah. But okay, I have one question put from the Thai translated channel. The team number 0081 would like to ask, is there any plan for using other materials for producing battery instead of lithium? Yeah. Is there any plan for other material, please?
So what within the group of lithium-based batteries, and we always have to be aware that maybe 3% of a lithium-ion battery is lithium. What is most expensive and rare these days is nickel and cobalt. And cobalt is already down to low percentages. What was 100% cobalt 30 years ago when lithium-ion batteries came to the market is only 10% or less these days anymore. And we expect at least in the second half of this decade also high-performance batteries without cobalt, at least for the automotive sector. Probably not in the stationary sector because they need much higher cycle lifetime, and we don't have high cycle lifetimes with pure nickel or manganese-based systems yet. And the other alternative is lithium iron phosphate, which goes beyond any nickel and manganese and cobalt, but at lower performance regarding the energy density. And then more or less the only thing I see until the end of the coming decade is sodium instead of lithium. CATL has announced to come this year with products, and there should be some prototypes somewhere, but I haven't had them in my lab yet personally. But this will be an option, at least in the cheaper cars, not in the highest performance cars because of lower energy densities. But this may unload a little bit the lithium market. I expect that the lithium technology will be much dominating the coming 10 years, but sodium-based batteries will probably start to really raise in the coming 2-3 years quite a bit. And beyond this, we don't really see things which are now ready. These solid-state batteries are lithium-ion batteries as today, just with solid instead of a liquid electrolyte. So this is not really a new battery technology and still has the same materials used more or less. But yeah, some people will see this as a new generation of batteries, but from the materials point of view, they are not.
Yeah. So we are coming to the end of the session. Maybe the last question, please.
Another question, please.
Yeah, the last question, please. Please.
Professor, as you mentioned in your page 32, so in Europe, why the amount of slow charging public stock is larger than fast charging public stock, but on the other hand, in China, the fast charging public stock is larger than the slow charging public stock. So what's your opinion about the fast charging? Is it not good for battery in Europe?
No, yeah, good point. I think, and if you look to the next slide with the averages, there's a certain difference. In Europe, the car manufacturers really try to go for very fast charging. Tesla has 150 kilowatt now as a standard. but Audi, Porsche, BMW, Mercedes, they want to go together with the European governments for fast charging infrastructure of 350 kilowatt. Therefore, the number of fast chargers is maybe relatively small, but the power rating is very high. Because it is expected that these public chargers are mainly needed if you go on highways. And today, the majority of the people who buy electric cars these days have houses on their own. So they have an own garage, and therefore they have a non-public slow charger at home anyway. So they will use mainly the chargers at home or the fast chargers on highway. Whereas if you look to China, if you look to the mega cities in China with these huge number of skyscrapers, where most people live in apartments and they do not necessarily have a garage on their own, they park their car somewhere. They need the public chargers also for their day-to-day charging. The day-to-day charging in Germany is not on public chargers, it is at home. But this is different in China. And therefore, when at the moment in Europe, I could say it is more the people with better incomes who buy electric vehicles. If we come to those having lower incomes and living also in skyscrapers or in apartment houses, the demand for probably chargers maybe 50 kilowatt will increase, but this is not so much the case right now. So I think it really depends on the different structure of housing which we have currently in Europe and in China that causes these differences here in the shares.
Thank you. Very clear answer, Professor.
All right, thank you very much. Now, because Professor Sauer must have another schedule, he has back-to-back meetings and so on. So I would like to express our deep gratitude to Professor Sauer, for spending time with us, giving very insights, full knowledge to all of the contestants who are the young generations who will enter the industry later on in the future. I believe the content that you have today would put inspiration to these people or to these students to go into our industry to help us develop our world better. Okay, thank you very much. You have any words to say to our students?
Many thanks for inviting me, and I hope that's really interesting to see at the end the outcome of this hackathon. And I really hope that lots of you will help us to really save our world at the end of the day. We need everybody who's going into the engineering science, into natural science, but also doing the business for these purposes. Because if we don't do anything very fast and very soon against the climate change, we all will suffer from it. And therefore, as Professor Nissa said, the young generation is our hope. And all the best to you, and good luck now for the hackathon at least. So thank you very much, and greetings to Thailand.
Yeah, bye-bye then. See you next time, Professor Sauer.
See you.
Thank you.
See you. Bye-bye.
Thank you very much. Thank you.
Bye-bye.
Bye-bye. Thank you very much.
Thanks a lot, sir.
Thank you very much.
Yep. See you. Bye-bye. Started. Nice to see you.